Next, we have conditional statements. And the first we are going to talk about is implication. Right, so we denote implication in this way, and we read this as either if P then Q, if P then Q, or another very common way to read this is P implies Q, right? So P implies Q. Now, there are subtleties to conditional statements. So we need to, first of all, be careful about the definition. You see the definition here. So you see in the output, all the outputs are true except for one scenario where P is true and Q is false. And that's the heart of the definition of implication. P implies Q is false only when P is true, but Q is false. Because if P implies Q when P is true, you would expect Q to be true. Okay. Now, let's look at the other alternatives or the other input combinations, because this is, I believe, easy to understand. When P is true, if Q is not Q is not true, you would expect P doesn't imply Q, right? There is no implication there. Therefore, it's only natural that this input combination should yield a false output. Let's look at some others. Obviously, this is also very easy to understand. When P is true and Q is also true, the statement P implies Q is also true. Again, this is a natural observation, right? P implies Q, and when P is true, you expect Q to be true. Therefore, the statement is true. Now, these are a little bit confusing, at least to some of my past students, let's say. Now, let's look at them separately, one by one. When P is false and Q is also false, why is the implication true? Okay, P is false and Q is also false, then P implies Q is true. This is a little bit, well, you see this in natural language when, for instance, in exaggerated statements, or maybe some statements that you use to attract attention, okay? For instance, if you can run 100 meters under 10 seconds, I can eat my hat, is an example, right? That's a true statement because neither of the components are true. But the implication is there. If you can do that, yeah, I can do this, right? Obviously, there is an element of exaggeration in this example, but from a logical point of view, the implication is there. And when P is false, as well as Q is false, the statement P implies Q is true. And I believe the input combination that leads to most confusion is this one. When P is false and Q is true, why is the implication true? If something is, okay, let's say this is false and this is true, then we say that there is implication between the two. P implies Q, right? And this is a little bit counterintuitive, but what you need to understand about implication is that the only case you don't have the implication is this one. When P is true, but Q is false, the implication is not there. Except for that scenario, the implication is going to be true because, well, when P implies Q, right, and P is not satisfied, meaning that it is false, it does not mean that it should prevent Q from being true. This is a very subtle point, but a very important one, okay? It could shape how you think about implications. When let's say the condition is not satisfied, then in that scenario, you don't really know anything about the expected outcome. Let me put it this way, okay? P being false doesn't really affect the value of Q. the definition of implication well, the scenario is significant when the condition, let's say P, is true. In that case, Q must be true so that we have an implication. But when P is false, the implication is going to hold whatever the value of Q is. Okay, so this is the definition of implication. And you see, when we talked about the implication there, I used the terms condition, the outcome, etc. Those are a little bit wonky terms that are not really appropriate. Let's use the proper terms here. P is called the antecedent of the conditional. Okay, I called it a condition. It's not really the proper term. The proper term is antecedent. P is called the antecedent, and Q is called the consequent. Okay, so these are the terms we use to describe in this setting, P and Q. And another important thing to recognize here is that P implies Q is equivalent to not P or Q. And we show that equivalence in this way. P implies Q is equivalent to not P or Q. Again, recall the rules of precedence here. This is not equivalent to not P or Q, right? This is equivalent to not P or Q. Be careful about this, but since unary operator takes precedence over or, we don't need the parentheses here. And why is this true? You can see this as building a new column to your truth table, and you can just compute the value of this using these input combinations, and you will see that these two have the same outcomes. Okay, so furthermore, you can express, especially in natural language, the implication in several different ways. If P, Q, Q if P, Q when P, or Q unless not P is another way to put it. Obviously, we talked about P implies Q, and you will encounter this in mathematical texts more frequently, or rather, Q follows from P. That's another way to put it. And P only if Q. You have to be careful about the order here. It's not Q only if P, it's P only if Q. Now, P and Q, you might want to think about this a little bit. There is not a typo here, right? It's actually if P then Q. That is the same as saying P only if Q, right? Maybe you might think about this a little bit. And these expressions or statements are all equivalent when we talk about implication.